Yeah, this is Math 105, section 3.2a. We're going to talk about polynomial functions and their graphs in this section. So we're going to look at how we graph polynomial functions. And just to recall, a polynomial function of degree n is a function of this form. P of x is a sub n x to the n. That would be our highest degree, whatever it is. And then this would be our next highest degree. Okay, a to the n minus 1, x to the n minus 1, etc. And then our last terms might be a1x plus a0. Now remember, we don't have to have all of these terms, but we do say that the first term, the n, if the degree is n, then we have to have that first term. So the coefficient's not going to be 0. Okay, so remember the numbers a0, a1, a2 are just the coefficients, and that means, like, you know, the x squared coefficient is a2, the x cubed coefficient is a3, etc. Okay. A0 is the constant coefficient, so that's the one that doesn't have an x with it, or constant term, we can say. And the number an is the coefficient of the highest power. Okay, we call that the leading coefficient. Okay, and then we say a sub n x to the n is the leading term. Okay, so that leading term is whatever the highest power of x is with its coefficient. Okay, so for example, here's a polynomial. Degree is 5. Our leading coefficient, a5, is 3. Okay. Here, this one, you know, we might have a x to the 4th term. We might have an x cubed term, x squared term, an x to the 1 term, and an x to the 0 term. So these are our other coefficients: 6 minus 2 plus 1, 7, and minus 6. Okay. Remember, the coefficients are just the number parts of each term. Okay, so here's some examples of polynomials. If, let's say let's look at the bottom one, 2x cubed minus 6x squared minus 10, that has a degree of 3. Our leading coefficient is 2. That's the highest power of x. This is a quadratic degree of 2. R of x equals x squared plus x. This is a linear function, a line. You know, think of y equals mx plus b, so q of x equals 4x minus 7. And then this would just be a horizontal line, y equals 3, so this has a degree of 0. So linear function could have a degree of 0 or 1. Quadratic will have a degree of 2. A cubic will have a degree of 3. Okay. If our polynomial has a single term, then it's called a monomial. Okay. So for example, p of x equals x cubed or q of x equals minus 6x to the 5th are called monomials. This one's a monomial here. Okay. Okay, so let's talk about graphing them. So the graphs of polynomials of degree 0 or 1 are just lines, okay, as we said. Polynomials of degree 2 are parabolas, they're quadratics, right? The greater the degree of polynomial, the more complicated its graph can be. In other words, we get more curves, like roller coaster type curves. Okay, but we can say that the graph of a polynomial function is continuous. Okay, that means that the graph has no breaks or holes. Okay, and in fact, it's going to be a nice smooth curve like this. It's not going to have any cusps either. It's going to be a nice smooth curve like a roller coaster curve, polynomial. Okay, for any polynomial graph. Okay, so the graph of a polynomial function is a smooth curve for degree 2 or greater. Has no corners or sharp points, no cusps. Okay. And then the simplest polynomial functions are the monomials, whose graphs are shown in figure 2. Okay. Let me just make a note there. This should be p of x equals x to the n power, not this one. Okay, so let's scratch that out. Okay. So the simplest polynomials are going to be the monomials, okay, whose graphs are shown in, we'll look at the next, well, this is x squared, right? Okay. This is y equals x, okay. So we're looking at x to the 1 and x to the 2, okay. Those are kind of the simplest polynomial graphs. That line, y equals x to the 1, and this is y equals x to the 2. Okay, we've looked at these before, but y equals x cubed is a monomial where our degree is 3. Right? Remember, it's a curve that goes up like this and then keeps going up. Okay, it has symmetry about the origin. Y equals x to the 4th. Remember, that's kind of the flattened, x squared flattened in the middle and stretched out in the ends, pulled up on the ends. Okay, and then x to the 5th would be a version of x cubed where it's flattened in the middle and stretched out on the ends, or it's pulled up or down on the ends. Okay, and we looked at these before, but this is kind of our basic polynomials. X cubed looks like this. X to the 5th looks like that, but it's flatter in the middle and stretched out. And then x to the 4th looks like x squared, but it's stretched out in the ends and flatter in the middle. Okay. So when n is even, let's kind of note that. So we can say the graph of p to the x equals x to the n has the same general shape as the graph of y equals x squared when n is even. and the same general shape as y equals x. That should be x cubed when n is odd. So let me put x cubed there, not x squared. So let's scratch that out. Okay. So when n is even, the degree is even, x to the n has the same general shape as y equals x squared, okay, x to the fourth. And when n is odd, has the same general shape as the graph of y equals x cubed. Okay. So here's an odd one. Here's the next odd one, x to the fifth. Okay, let's start with our first example. Will be p of x equals minus x cubed. So we're going to start with x cubed, which is the blue dotted one here, as we know. And then when we're changing x cubed to minus x cubed, we're changing our y. Remember, this is our y, this p of x. Okay, so we're changing our y to the opposite, which means we reflect across the x-axis. So we're going to take the blue dotted one and reflect it across the x-axis. So this blue would become the red here, and this blue dotted would become the red here. Now, you may notice that if you reflect it across the y-axis, you get the same graph, and that's not because, well, we're technically because we're also changing x to minus x in this function as well. It would give us the same result, but also because it has symmetry about the origin. So in this case, it doesn't matter which axis you reflect across, but generally when you're changing your y to the opposite, you're reflecting across the x-axis. Okay, our next one we'll look at q of x equals x minus 2 to the fourth. So we're going to start with x to the fourth, which remember is the x squared curve, but it's flatter in the middle between minus 1 and plus 1, and then it's stretched out more in the ends. So that'll be the blue dotted one, x to the fourth. And then we're changing x to x minus 2 in our function, which means we're moving it 2 to the right. Remember, when you replace x with x minus 2, you're moving it 2 to the right. Okay, and the next one we'll look at is r of x equals minus 2x to the fifth plus 4. Okay, so we're going to start with y equals x to the fifth. Okay, and that's going to be x to the fifth, which, remember, it goes down like this. Okay, it's actually going to be kind of like this blue dotted one. So it's going down like this. Okay, and it's flatter in between. It's like x cubed, but it's flatter between minus 1 and plus 1. Okay, then we stretch it vertically because we have a 2 there. So we would stretch that. Okay. So 2x to the fifth would look something like this. Here, I'll just draw it in here so we have it. 2x to the fifth would look something like this, kind of stretched out. Sorry, I didn't do that. Let me redo that. 2x to the fifth looks kind of like this, okay, kind of stretched out. Okay, so let's say that's 2x to the fifth. Sorry, I'm not drawing it very well. Okay, and then what we do is we reflect it across the x-axis because we're changing our y from 2x to the fifth to minus 2x to the fifth, so we reflect across the x-axis. So the black one becomes the blue dotted one. Okay, reflect across the x-axis, we reflect across the x-axis there. Okay, so now we have this, y equals minus 2x to the fifth. We already did the stretching on x to the fifth to get this, by the way. Okay, and then finally we just add 4. So remember, vertical shifts should be last. So now we're going to just take that blue one and move it up 4, and that's how we get the red. So that's our final graph, is minus 2x to the fifth plus 4. Okay, now let's talk about end behavior. So the end behavior of a polynomial is what happens as x becomes large in the positive or negative direction. Okay, so if you think about way out to the right or way out to the left, what's happening to the graph? So way out to the right would be x approaching infinity. Okay, so x becomes very large in the positive direction. Way out to the left would be x approaches minus infinity, which means x becomes large in the negative direction. We want to know what's happening to that graph. So that's what we mean by end behavior. Okay. So end behavior is always determined by the leading coefficient and leading terms, the term that contains the highest power of x. Okay, because the reason for that is because when x is large, which is what we're looking at, large, positive, or negative, the other terms are relatively insignificant. They don't really matter. So we're really only looking at the first term when we're talking about end behavior. Okay, so the first term, the one with the highest power of x, tells us what happens at the ends, okay, where x is very large, either on the positive or on the negative side. Okay, so here's some examples of what can happen. Looking at our general polynomial, okay, and if p has odd degree, okay, meaning the first term of highest degree is like a 3 or a 5 or a 7, that means it's going to go like this. It's going to go up to the right and down to the left, or vice versa. It could go up on the left and down on the right. So we're not worried about the dotted stuff. That's not what we're talking about. We're talking about the red, the solid red here. So, and these should technically be arrows here. So I'm going to put arrows there because that's really important that we have that there. Okay. So, yikes. Okay, this goes up and up. We'll look at that one in a second. This goes down and down. Okay, so for odd degree, it's going to go up in one direction and down in the other. And so it could be going up on the right or down the left, or vice versa. Okay. For even degree, like x squared, x to the fourth, and remember, we're just looking at the first term. It's either going to go up and up, like x squared or x to the fourth, or down and down, like minus x squared or minus x to the fourth. Okay, so let's look at this example. P of x equals minus 2x to the fourth plus 5x cubed plus 4x minus 7. Our first term is minus 2x to the fourth, so we have a degree of 4, which means it's an even degree. So our end behavior is going to be, now because it's minus 2x to the fourth, think about what minus x to the fourth looks like, right? It's minus x to the fourth looks like this. Okay. Y equals minus x to the fourth looks like this because we're reflecting, right? So it's going to be kind of that flat parabola going down like this. Okay. So that's what it's going to look like on the end behavior. It's going to look like this and this on the ends. Okay. So it's going to look like minus x to the fourth or minus 2x to the fourth. Okay. So that means as y approaches minus infinity, as x approaches plus infinity. So that's to the right there. Okay, y approaches minus infinity. And then y approaches, this should be a minus here as well. Y approaches minus infinity as x approaches minus infinity. So you see y going down in both cases. This should be a minus infinity and this should be minus infinity. Okay. So that's because we have a degree of 4. Okay. The leading coefficient of minus 2 tells us it's going down and down. Okay. So we're talking just about the end behavior, not what's happening in between here. Okay, so this is what our graph looks like for that minus 2x to the fourth plus 5x cubed plus 4x minus 7. As x approaches minus infinity, so does y, and then as x approaches plus infinity, y goes to minus infinity as well. So you can see it's going down and down. And this is, you can see in the middle the graph is doing something different than minus 2x to the fourth or minus x to the fourth, and that's because we have these other terms here. But you know, the important thing is that on the ends, really all that matters is that first term, minus 2x to the fourth, and it's going to look like, you know, minus x to the fourth or minus 2x to the fourth on the ends here.